Hello everyone, my name's Iman. Welcome back to my YouTube channel. In today's video, we're going to discuss heating curves and learn how to calculate the energy involved in both temperature changes and phase changes. After that, we're going to revisit enthalpy and show how to calculate the enthalpy change of a reaction using bond energies, standard enthalpies of formation, and Hess's law. Let's begin with the first topic, heating curves. A heating curve shows how the temperature of a substance changes as heat is added. On the x-axis of this curve, we have the amount of heat added, and on the y-axis, we have the temperature. As we supply energy, the substance progresses through various physical states, from solid to liquid to gas. And the curve you notice contains sloped segments where temperature increases and flat segments where the substance undergoes a phase change. During the sloped regions, heat increases the kinetic energy of the molecules, which leads to a rise in temperature. However, during the flat regions, heat does not change the temperature. Instead, it's used to overcome intermolecular forces and convert the substance from one phase to another. These phase transitions, which happen in segment 2 and 4, each have an associated enthalpy value. During melting, where we go from solid to liquid, the heat required is called the enthalpy of fusion. And then during boiling, where we go from liquid to gas, the heat required is the enthalpy of vaporization. Both are constants that represent how much energy per gram is needed to complete the phase change. Now, if we were removing heat instead of adding it, that means we're cooling instead of heating, then the curve would be traced in reverse. The reverse of vaporization is going to be condensation, going from gas to liquid, and the reverse of melting is freezing, going from liquid to solid. With this background information, let's go ahead and walk through each segment of the heating curve in detail, starting with segment 1. In segment 1, the substance is in its solid state. Let's take ice as an example. As heat is added, the particles begin to vibrate more rapidly. That increases their kinetic energy and therefore raises their temperature. The equation that's used here to calculate heat is Q is equal to mc solid delta T, where m is the mass of the substance, C solid is the specific heat capacity of the solid phase, and delta T is the change in temperature. For ice, that value, C solid, is equal to 2 joules per gram times Celsius. Once the solid has reached its melting point, we then enter segment 2. For ice, the melting point is 0 degrees Celsius. And at this point, heat continues to be added, but the temperature no longer increases. Instead, that energy goes towards breaking the intermolecular forces that hold the solid structure together. And that helps convert the substance into its liquid form. This is a phase change. So that means our equation to calculate heat is going to look a little different. For segment 2, to calculate the heat, Q is equal to mass multiplied by the enthalpy of fusion. This is the heat required to convert 1 gram of solid into liquid at constant temperature. For ice to water conversion, the enthalpy of fusion is equal to 340 joules per gram. Segment 3 begins once all of the solid has melted. So based off of our current example, the ice would be liquid water in this segment. Additional heat here, once again, increases the kinetic energy of the particles, and that raises the temperature, hence why it's a sloped segment. The equation used to calculate heat for segment 3 is Q is equal to M multiplied by C liquid multiplied by delta T. It follows the same form as segment 1, but now we use the specific heat capacity of the liquid. For water, this value is about 4.18 joules per gram times Celsius. Once the liquid reaches its boiling point, we now enter segment 4. So for liquid water, the boiling point is 100 degrees Celsius. Heat is added to convert the liquid into gas, and the temperature remains constant while this phase change occurs. The equation used is going to be Q is equal to mass multiplied by the enthalpy of vaporization. For water, this value is significantly larger than the enthalpy of fusion because it requires more energy to completely separate particles into the gas phase due to stronger cohesive forces in the liquid. And for water, this is going to be equal to 2,260 joules per gram. Finally, we have segment 5, which represents the gas phase. Once all of the liquid has vaporized, additional heat is going to increase the temperature of the gas, and we can use this equation to calculate the heat. Heat is equal to M multiplied by C gas delta T. C gas is the specific heat capacity of the gas phase. For water vapor, that is going to be 2 joules per gram times Celsius. So to summarize, the phase changes always occur at constant temperature, and they involve enthalpy values, while temperature changes within a single phase are calculated using the specific heat equation. Each segment of the curve has to be treated as a separate step. So if a problem asks for the total heat absorbed over several segments, you're going to need to calculate the value of Q for each segment individually and then sum them to get the total. Let's put this into effect by tackling a practice problem. This one says, use the following thermodynamic values to solve the heating curve calculation. We're told that the water has a heat capacity of 4 joules per gram times Celsius. Ice has a heat capacity of 2 joules per gram times Celsius. Steam has a heat capacity of 2 joules per gram times Celsius. Water has a heat of fusion of 300 joules per gram, and water has a heat of vaporization of 2,200 joules per gram. The melting point of water is 0 degrees Celsius, and the boiling point of water is 100 degrees Celsius. How much heat is required to convert 8 grams of ice at -5 degrees Celsius to liquid water at 50 degrees Celsius? To solve this, we need to identify all the steps involved and then calculate the heat required for each one individually. So we start by recognizing that the process includes 3 segments of the heating curve. First, we need to warm the solid ice from -5 degrees Celsius to 0 degrees Celsius. Second, we're going to melt the ice at 0 degrees Celsius into liquid water. And then finally, we warm the liquid water from 0 degrees Celsius to 50 degrees Celsius. Each of these steps uses a different equation and thermodynamic value, so we're going to calculate them separately, and then we're going to add them together to get the total heat required. We'll begin with step 1. Step 1 is the warming of solid ice from -5 degrees Celsius to 0 degrees Celsius. Since this is a temperature change within a single phase, we're going to use our equation Q is equal to mass multiplied by the specific heat capacity of the solid multiplied by delta T. The mass is 8 grams. The specific heat capacity of ice is 2 joules per gram times Celsius. So we can plug that in. And then delta T is going to be final temperature minus initial temperature. So that's going to be equal to positive 5. If we plug this into a calculator, we're going to get 80 joules. So that is the heat required for step 1. Now let's do step 2. Next is the phase change from solid to liquid, and this occurs at 0 degrees Celsius, so it requires enthalpy of fusion to calculate. Since temperature remains constant, our equation is Q is equal to mass multiplied by the enthalpy of fusion. We have both of these values. Mass is 8 grams, and the enthalpy of fusion, as given to us, is 300 joules per gram. When we carry out this calculation, we get 2,400 joules. Now we can move into our third and final segment. Here we're going to warm the liquid water from 0 degrees Celsius to 50 degrees Celsius. Again, this is a temperature change within a single phase. So the equation we're going to use is Q is equal to mass multiplied by the specific heat capacity of liquid multiplied by delta T. The mass is 8 grams. The specific heat capacity of liquid water is 4 joules per gram times Celsius. And then delta T is final temperature minus initial, so 50 minus 0, which is 50. When we carry out this calculation, we get 1,600 joules. To find the total heat required for the entire process, we simply add together the Q values from each step. So Q total is 80 joules plus 2,400 joules plus 1,600 joules. And this gives us a total of 4,080 joules. The total heat required to convert 8 grams of ice at negative 5 degrees Celsius to liquid water at 50 degrees Celsius is 4,080 joules. Now that we've explored heating and cooling curves in detail, let's return to the concept of enthalpy. Enthalpy, denoted as delta H, is defined as the total heat content of a system at constant pressure. It represents the energy absorbed or released by a system during a chemical or physical process, and it's a central concept in thermochemistry. When we examine chemical reactions, we often focus on how the enthalpy of the system changes from reactants to products. And this change in enthalpy gives us insight into whether the reaction releases or absorbs energy. If a reaction releases energy to the surroundings, it's called an exothermic reaction. In an exothermic process, the products have lower enthalpy than the reactants, so delta H is negative. This means that heat is given off during the reaction, often resulting in a temperature rise in the surroundings. In contrast, an endothermic reaction absorbs energy from the surroundings. In this case, the products have higher enthalpy than the reactants, so delta H is positive, and the surroundings typically cool down as energy is being taken in to drive the reaction forward. The graphs that are shown here help us visualize the difference between these two types of reactions. On the x-axis, we have the reaction progress or coordinate, and on the y-axis, we have the energy of the system. For an exothermic reaction, you'll notice that the energy of the reactants is higher than that of the products, and the gap between them represents the magnitude of delta H, which is going to be negative. For an endothermic reaction, on the other hand, the energy of the products is higher than the energy of the reactants, and this gap reflects a positive delta H. To this point, the enthalpy change for a chemical reaction, delta H of reaction, it represents the net energy exchanged between the system and surroundings over the course of the entire reaction. And there are multiple ways we can determine this value. One approach is to measure it directly in the lab using calorimetry, such as constant pressure or constant volume calorimetry, both of which we discussed in the previous lecture. Alternatively, we can calculate delta H reaction indirectly using a few different strategies. We can use bond enthalpies, we can use standard enthalpies of formation, or we can apply Hess's law by summing reactions that lead to the overall target reaction. These three calculation methods will be the focus of the remainder of this lecture. Let's begin with our first method for calculating enthalpy change using bond enthalpies. A bond enthalpy, sometimes called bond dissociation energy or BDE, is the amount of energy required to break 1 mole of a particular type of bond in the gas phase. In other words, it tells us how much energy it takes to completely separate the atoms in a chemical bond when everything is in the gas state. Because breaking bonds requires energy input, bond breaking is always an endothermic process. On the other hand, forming bonds releases energy, so bond formation is an exothermic process. To calculate the enthalpy change of a reaction using bond enthalpies, we use the following formula. This equation tells us that we're going to sum the bond enthalpies of all of the bonds broken in the reactants, which requires energy, and then subtract the sum of the bond enthalpies for all the bonds formed in the products, which releases energy. The result gives us the net energy change of the reaction. Positive if the reaction overall absorbs energy and is endothermic, and negative if it releases energy and is exothermic. The best way to understand this is to apply it to a practice problem. So this problem says, use bond enthalpy data and calculate the change in enthalpy for the following reaction. We have methane reacts with 2 moles of oxygen gas, and that gives us carbon dioxide and 2 moles of water vapor. So we want to first draw out the reactants and products. This is really important so we can determine which bonds are broken and which bonds are formed as this reaction proceeds. So we want to identify the bonds in the reactants. First, in methane, CH4, this is what it looks like. We have 4 carbon-hydrogen bonds. And then we also have oxygen gas. Oxygen gas has a double bond. So for 2 oxygen gas molecules, we have 2 oxygen double bonds. So on the reactant side, we're breaking 4 carbon-hydrogen bonds. This is really important. And we're also breaking 2 oxygen-oxygen double bonds. On the product side, we have carbon dioxide. Carbon dioxide has 2 carbon-oxygen double bonds. So we're going to be forming 2 carbon-oxygen double bonds. Then we're also forming 2 water molecules. Each water molecule has 2 oxygen-hydrogen bonds. And when we have 2 water molecules, that's a total of 4 oxygen-hydrogen bonds that we're forming. Now that we understand what we're breaking and what we're forming, we're going to plug in the bond enthalpy values to get the total for bonds broken and get the total for bonds formed. If we are breaking 4 carbon-hydrogen bonds and each carbon-hydrogen bond requires 413 kilojoules per mole, that's going to be a total of 4 times 413, and that's equal to 1,652 kilojoules. So this is the amount of energy required to break 4 carbon-hydrogen bonds. What about the energy required to break 2 oxygen-oxygen double bonds? Each oxygen-oxygen double bond requires 498 kilojoules per mole. So for 2 of these, we're going to need 996 kilojoules. So the total energy input to break all of these bonds is going to be 1,652 plus 996. So this is equal to 2,648 kilojoules. Now, what about the bonds formed? So we're going to form 2 carbon-oxygen double bonds. A carbon-oxygen double bond is going to release 799 kilojoules per mole. So for 2 of these, it's going to be 2 times 799. This is going to be equal to 1,598 kilojoules. What about our 2 water molecules? We will form a total of 4 new oxygen-hydrogen bonds. Oxygen-hydrogen bond, we have 463, so we multiply that by 4, and we will get 1,852 kilojoules. So the total energy released from all of these bonds forming is going to be 1,598 plus 1,852, and that is equal to 3,450 kilojoules. So we now have total energy input for bonds broken and total energy released for bonds formed. We can calculate, finally, the enthalpy change. Delta H of the reaction is going to be the bonds broken, 2,648 kilojoules, minus bonds formed, 3,450 kilojoules. And this gives us a final answer of negative 802 kilojoules. This negative value indicates that the reaction is exothermic. It releases 802 kilojoules of energy for every mole of methane combusted. It's important now to note that bond enthalpy calculations are an approximation. The bond energies we use are average values taken across many different molecules, and they also assume that all of the species are in the gas phase, and that's not always true in real chemical reactions. So, with this consequence in mind, we're going to cover a different way to calculate enthalpy change. So because of these limitations that we just discussed, chemists often turn to another method for calculating enthalpy change, one that uses experimentally measured thermodynamic data called standard enthalpies of formation. And this is what we're going to cover next. The enthalpy of formation is the enthalpy change that occurs when exactly 1 mole of a compound is formed from its elements in their most stable form under standard conditions. And these standard conditions are 298 Kelvin and 1 atmosphere of pressure. The subscript circle in our notation of the enthalpy of formation is a reminder that the value applies under these standard state conditions. To calculate then the standard enthalpy change for a chemical reaction using heats of formation, we're going to use the following equation. This equation tells us that we take the sum of the enthalpies of formation for all of the products, each multiplied by its stoichiometric coefficient, and then subtract the corresponding sum for the reactants. Here, it's essential to remember that the enthalpy of formation for any element in its standard state is 0. So that includes things like oxygen gas, hydrogen gas, nitrogen gas, and solid carbon in the form of graphite. All of their enthalpy of formation is going to be 0 since the elements are in their standard state. Now, a lot of this might not make sense, but it will become more clear once we apply it to a practice problem. So that's exactly what we're going to do. This problem asks us to calculate the standard enthalpy change for the following reaction between calcium carbonate and hydrochloric acid. We're given the standard enthalpies of formation for each compound involved. And we're going to use our equation to solve this. The first part is we're going to figure out what this term is. So that means we need to calculate the total enthalpy of the products. So we'll focus on the products. Our first product is calcium chloride, and we form only 1 mole of calcium chloride. So the enthalpy of that product is going to be 1 mole multiplied by the enthalpy of formation for calcium chloride, which is negative 877.1 kilojoules per mole. And this is just going to be equal to negative 877.1. Then we also form 1 mole of water, and the enthalpy of formation for water is equal to negative 285.83 kilojoules per mole. So when this is multiplied by 1, it's really easy. This is just equal to negative 285.83. Then finally, we also form 1 mole of carbon dioxide. And the enthalpy of formation for carbon dioxide is negative 393.51 kilojoules per mole. So this is equal to negative 393.51. The total products is going to be the sum of all of this, and that will give us negative 1,556.44 kilojoules. So this is the following term in our equation. Now we have to figure out the same thing for the reactants, and then we can take that value for products minus reactants to get our final answer. For our reactants, we form 1 mole of calcium carbonate, and the enthalpy of formation for calcium carbonate is negative 1,206.9 kilojoules. When we multiply this by 1, it's still negative 1,206.9. And then we also have 2 moles of hydrochloric acid in our reactants. The enthalpy of formation for hydrochloric acid is negative 167.16 kilojoules per mole, and this gives us negative 334.32. For the total reactants, if we sum this up, we get negative 1,541.22 kilojoules. And with that, we can now finally plug everything into our equation and calculate delta H of the reaction. This is going to be equal to negative 1,556.44, which is what we calculated for the products, minus what we calculated for the reactants, which is negative 1,541.22 kilojoules. And this gives us a final answer of negative 15.22 kilojoules. So the standard enthalpy change for this reaction is negative 15.22 kilojoules, meaning the reaction releases energy and it's exothermic. Now that we've learned how to calculate enthalpy changes using both bond enthalpies and standard enthalpies of formation, we're ready to explore the third and final method, which is Hess's law. This approach is particularly useful when we aren't given bond energy values or formation enthalpies directly, but instead we're provided with multiple related chemical equations and their associated delta H values. The principle behind Hess's law is rooted in the fact that enthalpy is a state function, meaning it depends only on the initial and final states of a system and not the path taken to get there. So if we can add up a series of reactions to match a desired overall reaction, we can also add their enthalpy changes to determine the overall delta H. The rule is simple. If a set of reactions add up to a target reaction, then the sum of their enthalpies give the enthalpy of that target reaction. And to apply Hess's law, we use a few tips and tricks. The first is that flipping a reaction reverses the direction of the process, so we also reverse the sign of delta H. If we multiply a reaction by a coefficient, that scales both the reaction and its enthalpy change by that same factor. And we then add the adjusted reactions together. We cancel out any species that appear on both sides until we match the desired reaction. And from there, we can add up the enthalpy changes for each of the given reactions to get the final enthalpy of that target reaction. Again, this is best understood by doing an example problem. So for this one right here, we want to calculate the standard reaction enthalpy, and we are given 3 reactions and their associated enthalpies. So we're going to manipulate these reactions to arrive at the target equation. We're going to start off simple. We're going to look at the target product. Here we have 2 moles of ammonia gas. That appears on the product side of reaction 3 as well, and it has the same number of moles. And this is the only place among the 3 reactions here where we see ammonia gas. Since they're both on the same side, they're on the product side, and they have the same number of moles, for now, we are not going to do anything to reaction 3. We're not going to flip the reaction, and we're not going to multiply the reaction by a coefficient. Next, we're going to start to look at the reactants a little bit. So one of our first reactants that we have is N2H4, and it's a liquid. And the only place this reactant appears in one of the 3 given reactions is in reaction 1. And it appears in the reactant side, just like we want it for our target reaction, and they're both just 1 mole. So that's perfect. Those line up perfectly. So for now, we're also not going to manipulate reaction 1 at all. We're not going to flip it. We're not going to multiply it or scale it by a coefficient. Now let's look at our second reactant here. We have hydrogen gas. Now, where does hydrogen gas appear in these 3 target reactions? It appears in several places, actually. Here in reaction 2, we have 2 moles of hydrogen gas on the reactant side. And then in reaction 3, we have 3 moles of hydrogen gas also on the reactant side. This is interesting. If we were to add these reactions up right now, we would end up with 5 moles of hydrogen gas on the reactant side. But we have to be clever. We have to manipulate these 3 reactions in a way where when they sum up, all we're left with is N2H4 and H2 on the reactant side and 2 moles of ammonia gas on the product side. So what can we do? Sometimes this takes a little bit of trial and error, but what I'm going to do right now is I'm going to flip this reaction. Reaction 2, I'm going to flip it. So that means the reaction is now that 2 moles of water vapor form 2 moles of hydrogen gas and 1 mole of oxygen gas. And because I flipped this reaction, we also have to reverse this sign for the delta H. So it's no longer negative 484 kilojoules per mole. It's now positive 484 kilojoules per mole. By doing this, I've accomplished a few things. The first thing is that we have 2 moles of hydrogen gas on the product side and 3 moles of hydrogen gas on the reactant side. And what happens when we sum this up is that they're going to cancel out. 2 moles are going to cancel out on both sides, and we will be left with just 1 mole of hydrogen gas on the reactant side, which is exactly what we want. So let's do that. Before we make any more manipulations to our reactions, let's sum everything up and let's see which things cancel out. So if we sum this up, N2H4, there's nothing for it to cancel out with, so it stays on the reactant side as is. Then we have this oxygen gas right here. Oxygen gas is not part of our target reaction. So what do we do? Well, the thing to notice is that in the second reaction, it appears on the product side. So whenever you're summing up these reactions, whatever it appears on both the reactant and product side actually end up canceling out. And you'll see the same thing happen with these 2 moles of water. It appears as a product and as a reactant, so they cancel each other out. And finally, same goes with the nitrogen gas. We have 1 mole in the product, 1 mole in the reactants. They cancel out. So now what we're left with is N2H4 in the reactants plus 3 moles of hydrogen gas, and that forms 2 moles of hydrogen gas plus 2 moles of ammonia. Now notice that 2 moles, 3 moles, these partially cancel out, and we're left with exactly what we want for our target reaction. So all we had to do was just flip this second equation, and everything canceled out appropriately to give us our target reaction. Now, we're not done yet. The final step is to figure out the sum for the enthalpy changes. It's going to be minus 543 kilojoules per mole plus 484 kilojoules per mole minus 92.2 kilojoules per mole. So just like we summed up our 3 reactions to get our target reaction, we do the same with the enthalpies to get the total enthalpy change for this reaction. And if you plug this into a calculator, you're going to get negative 151.2 kilojoules. So the standard enthalpy change for this reaction is negative 151.2 kilojoules. And with that, we've completed this lecture. I hope this has been helpful. Please let me know if you have any questions, comments, concerns down below. Other than that, good luck, happy studying, and have a beautiful, beautiful day.